Welcome to lecture 41 of the course Modeling and TCAD Simulation of Solar Photovoltaic Cell. This is the first class of 9th week. In this class, we continue the numerical solution of semiconductor equations. That's why this is a part 2. In last lecture, we have discussed about the solution of differential equations by finite difference method, and we have also shown you the example. There is a one-dimensional Poisson's equations. This is a simple differential equation in one dimension. How it can be solved by taking an numerical problem we have discussed. In this lecture, we will discuss the solution of two-dimensional Poisson equation by iterative method. So let us start solving Poisson equation iteratively. The steps are, first you have to discretize the equation using a finite difference method to create a system of linear equations that already we have discussed in earlier classes. Then we have to apply the iterative method, maybe Jacobi or Gauss-Seidel. These are two well-known methods for iterative solution of Poisson equation. We have to start with an initial guess for the solution at each grid point. If the boundary conditions are given for some grid points, that is values at some grid points, we don't need to guess for those nodes. But the nodes which are not related to the boundary condition, that is values are not given, we have to have an initial guess. Then, based on the equations, there is a linearized equations, we have to repeatedly update the values using the discretized equation until the solution converge. Converge means when the values of any particular node does not change significantly from the last iteration, we have to stop. So that is the condition for convergence. We can set some condition, say difference between kth iteration and k plus 1th iteration must be less than equal to 0.001. Then we will stop. So in this way you can set condition through numerical through programs in computer. Then it is stopped only if this condition is satisfied. Actually, there are two methods. In the Jacobi method, updates of each node's value is based on the values from the previous iteration. While in Gauss-Seidel updation, that is based on the most recently updated values. It will be more clear when we will discuss through an example. And the Gauss-Seidel methods provides a faster convergence. Actually, in Gauss-Seidel method, we update the node values, and in the right hand side of any equation of a node values, we can use the very recently updated values even in the same iteration. But in case of Jacobi method, the updation of node values are based on the previous iteration only for all the nodes. So let us start the iterative method, but before that we have to discretize the equation for two-dimensional Poisson equation with some particular structure or particular domain of a device. So first we have to fix the mesh structure. That is, mesh nodes at the boundary and mesh nodes at the interior points. And if you have the boundary conditions for the nodes at the boundary, you don't need to have an initial guess for those. But for interior nodes, you have to guess the initial values. So for example, if you have a domain of device, suppose this is a square domain, you are dividing these into several nodes at equal distance, although the figure is not actually mapping, but you consider the distance between node points along x-axis and along y-axis, both are equal, and also the values of delta x from one node to another next node are equal. So these are the nodes at the boundaries. And if boundary conditions are given, suppose in this plane, say boundary condition is, say, phi is equal to 0. Suppose this is the phi is the potential. For this left node, suppose also phi is equal to 0. This is also, say, phi is equal to 0. But here the nodes are, say, phi is equal to 100. Suppose in that case, the node value here, 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 and these 5 node values have an initial value 100, but the boundary condition. But other nodes, other surfaces may be 0. This may be a particular boundary condition. But what are the interior nodes? These are the interior nodes. This one. So these interior nodes, you have to have a initial guess. An interior node, say ij, at any interior node ij, the finite difference Poisson equation is del square phi is equal to f. F is a function of xy, and that includes the negative sign, all these things. Any node, interior node, suppose this is, you are noting as ij. So obviously this node will be I minus 1 comma j. This node will be I plus 1 comma j, in this way. Similarly, along y direction increment, that is, this node will be I comma z plus 1. This node will be I comma z minus 1. In this way, we will be proceeding. Now the formula for the second order derivative at node, say, phi j, this can be written in this way. Phi ij, that is 1 by 4, phi I plus 1 j, that is this value, plus phi I minus 1 j, this value, plus phi I j plus 1, this value, plus phi I j minus 1, this value. So 1/4 of values surrounding the node ij. This is called discrete 5-point formula, and this formula, if you apply, the 5 point will be coming here, because this point is at center, and around surrounding that there are 4 points. So there is a total 5 points. So this is called discrete update 5-point formula. And this basic formula will be used by, say, Jacobi and Gauss-Seidel, or successive over relaxation method. That is also a modification of Gauss-Seidel method with some particular weight. So this formula for the derivative in 2 dimension will be used. So let us describe the iterative method. Now the schemes are classified into different categories based on the update rules. Say for Jacobi method, update of the node at the k plus 1th iteration will be 1 by 4. That will be from the earlier iteration k, phi I plus 1 node k, phi I minus 1 j for kth iteration. So all these values from the previous iteration, it is used to compute the new value of phi ij at this node. And k indicates the iteration number. For Gauss-Seidel method, the update is also in this way, but arrow sign indicates here, say whenever you are computing the value at node ij, that is phi ij, by using the nodes in its left side, right side, in next below node and next upper node. But if whenever you are doing this, say first time, say for a node, particular node, you can get these other nodes are from the previous one. But during this process, if any node value, say I plus 1 j node, is already updated in the same iteration, then that value of latest updated value should be used in calculating the phi ij at k plus 1. It will be more clear whenever we will be doing this through some example. And in this case, as in Jacobi there are fixed old values always for kth iteration, but here it is not for kth iteration. This may be for kth or even k plus 1th iteration. So this node values, latest updated value should be putting. Similarly here also, this may be kth or this also, this also. This is one update from the one additional feature of the Gauss-Seidel method. And in place, update in place, that is using the newest available values immediately. That is very important. And in successive over relaxation, SOR method, this basically accelerate the Gauss-Seidel method with a relaxation parameter W, say. W, so phi ij at k plus 1 iteration is basically done by a factor, that is 1 minus W into phi ij k plus W in other values from the previous iteration. However, W, the value of W, choice of W is very crucial for achieving the convergence. So a commonly used estimated value or nearly optimal value of W generally is given as 2 by 1 plus sine pi h, where h is mesh spacing. Now let us consider the two-dimensional Poisson equation and use the 5-point finite difference method or form of equations. So let us consider the two-dimensional Poisson equation, del square phi del x square plus del square phi del y square is equal to minus q by epsilon 0 epsilon rs p minus n plus nd minus na. And this total function, say this is function of x, y, because this is also position dependent. All the nodes has a different, may have different charge, may have different donor concentration, acceptor concentration, etc. So in general, it can be written as fxy. If fxy is 0, this becomes Laplace Poisson. Poisson Laplace. That is, in that case, f is 0. In right hand side, it will be 0. So let us now write down the 5-point formula. Suppose this is a structure. This one interior points, say ij, I have noted, and h is equal to delta x, H y is equal to delta y, both are equal. Now if we write the equation, this del square phi del x square plus del square phi del y square, considering this node, first let us del square phi del x square. What is the value? We know this value. We know this del square phi del x square value at ij node, that will be in left side node, this node, that is phi I minus 1j, this is phi I minus 1j, plus phi I plus 1j, this node value, minus twice the phi ij, this value, twice phi ij, by h square. This is the del square phi del x square formula. Similarly, del square phi del y square, that will be the value at upper node or lower node, whatever you consider. This lower node, this value, phi I j minus 1, potential here, plus potential here, minus twice the phi I j, that is phi I j plus 1 minus twice phi I j by h square. This gives you the derivative along y axis, and this is along x axis is del square phi del x square. So this is the total del square phi del x square plus del square phi del y square. So if we combine them, ultimately it is coming h square phi I minus 1 j plus phi I plus 1 j plus phi I j minus 1 plus phi I j plus 1 minus 4, this and this 4, phi I j. So this is here the double derivative means this node value plus this node value plus this node value plus this node value minus 4 times this node value divided by h square, that will be equal to the right hand side. This is Fij. Say Fij simply you can write at node ij. So function right hand side function is at a node ij. So this is the 5-point formula you can use in this way, and we will apply this to solve a particular problem. Now, for remembering these things, you can use this, you can have these types of figure. Suppose you have a notation like this. This is a central point is minus 4, left node 1 coefficient is appearing, right node also in 1 coefficient is appearing. This is 1, and top is also 1 and bottom is also 1. So this node value with a weightage, it can be remembered in this way, minus sign indicates. So this is the 5-point technique in this way. So let us now consider a specific example. Say we have a equation for Poisson equation for a device, say where the region, you have a region where only acceptor ion. So that means you can consider a depletion region, depletion layer within a device. Suppose you have a depletion region within P region. So this is suppose whole region. So this is our whole P region, this is our whole N region, and this is the depletion region, inside P. So in this region, the shaded region, that is a part of a PN junction. The junction point, from the junction point to the end of depletion region within P region, that is suppose our region of interest. So the Poisson equation, del square phi del x square plus del square phi del y square, that will be equal to minus q by epsilon, that is epsilon 0 into epsilon rs, minus Na, because only we are considering here the acceptor ions are present. So this may be written as f of xy. But in this case, this is a constant. This is a constant in this case. For this example, this may be constant here. We have to first discretize this portion, and let us consider in this way we are discretizing the thing, and some boundary conditions we are considering this. So this point, starting from this to this, we are dividing into a square mesh. So this point is say 0 0, this is 1 0, 2 0, 3 0, and this is 0 1, 0 2, 0 3. So other points are also mentioned, and boundary points are on the dash line and interior points are on the solid line. So 1 2, 2 2, 1 1, 2 1, these four are interior nodes and rest nodes are suppose boundary, and nodes are the boundary. And the boundary condition we are considering, suppose this boundary is phi is equal to 0. At this boundary, left boundary also phi is equal to say 0. In the top boundary also phi is equal to 0. But in the right side, this boundary, let us consider phi is equal to 100. Say 100. Okay, let us consider 10. It is 10. No issue. You can consider 100 or 10, but for ease of calculation, we are taking this 100, 10. First of all, we have to concentrate on the interior nodes, starting from 1 1, then 1 2, then 2 1, then 2 2. Let us consider H, that is a mesh spacing, that is also 1, that is delta x is equal to delta y is equal to 1. For again simplicity of calculation, we are considering h is equal to 1. Now this node is again reproduced here for writing the node equations. How can we write? First, let us write the node equation for the 1 1 node. Say for node 1 1, phi 0 1 1 1. What is the differentiation of this 1 1? 1 1 means del square phi, say del square phi del square del x square plus del square phi del y square, that will be equal to f of xy for node ij. Now this left portion will be phi 0 1 plus phi 2 1 minus 2 into phi 1 1, and this portion will be phi 1 0 plus phi 1 2 minus 2 phi 1 1, but combining as I have shown in last slide. So this left hand side full two-dimensional Poisson equation, we can write phi 0 1 plus phi 2 1 plus phi 1 0 plus phi 1 2 minus 4 phi 11 divided by h square, that will be equal to the f11, and f11, say this constant is suppose 100 and h is 1, so h square, actually this h square is taken in the right hand side, so I am just showing how it is coming. So left hand side it was phi 01 plus phi 21 plus phi 12 plus phi 10 minus 4 phi 11 divided by h square, that will be equal to 100, say 100 means, let us consider the constant value that I have mentioned, the f xy, that is equal to constant 100, that is a charge constant 100 value. That means here the value we are considering the fxy, that is minus q by minus q, this is minus q by epsilon 0 epsilon rs into minus na minus. So total value, suppose this is a constant, because in this region we are considering the value of na is constant, and this constant we are taking as a 100, say this constant value, so this is equal to 100, say. So that's why we put this value as a 100 here. So let us, this is equation number n1, or not 1 because n is to distinguish from the earlier equation number 1 for our lecture, for this course. So if you just left hand side, if you multiply the denominator with the right hand side, it will be 100 h square, h is 1, so 100 into 1 square. So this is the equation formed for the node phi 11. Similarly for node say 2 1, this is the node suppose 2 1. What is the node 2 1? This is suppose node 2 1, this node. This node value again phi 11 plus phi 31 plus phi 20 plus phi 22 minus 4 into phi 21 is equal to 100 into 1 square. That is written phi 11 plus phi 11 plus phi 31 plus phi 22 plus phi 20 minus 4 times phi 21 is equal to 101 square. Similarly for this node, say 1 2 node, let us write phi 02, this node, so this will be phi 02 plus phi 22 plus phi 13 plus phi 11 minus 4 times phi 12 is equal to 100 into 1 square. This is equation number n3. And for 2 2 node, again the same process, left node plus right node plus node at top and plus node at bottom, that is below this, minus 4 times. So again the same thing, phi 12 plus phi 32 is phi 12 plus phi 32 plus phi 23 plus phi 21 minus 4 phi 22 is equal to 101 square. These 4 equations are linearized equations we have obtained. Now how can we proceed this? Now you can put the boundary condition. What are the boundary condition? Already I mentioned that these planes are 0. So for this, say boundary condition like this, say phi 0 0 is equal to 0, phi 10 is 0, phi 20 is 0, but phi 30 is not 0 because right side plane phi is equal to 10. And also phi 01, phi 02, phi 03, phi 13, phi 23 all are 0. But these values is phi 30, phi 31, phi 32 and phi 33, that is 30, 31, 32, 33, that is equal to 10. So put these boundary condition, that is these node values, into the equation n1 to n4. So boundary condition if you put in n1, so n1 becomes say 5, say here you see n1, the phi 01, phi 01 will become, if you see phi 01 value, phi 01 is 0. So this is 0. I can write this is 0. Phi 21 value, if phi 21 is interior node, okay, leave it. 1 2 is also interior node, leave it. 1 0, again phi 10. Phi 10, phi 10 is 0. This is 0. Phi 11 is there. So ultimately it reduces to phi 21 plus phi 12 minus 4 phi 11 is equal to 100. That is written here. You see, phi 2 1 plus phi 1 2 minus 4 phi 1 is equal to 100. So it becomes now 3 unknowns. Similarly, the other equation, say n2 becomes 4 phi 2 1 plus phi 2 2 plus phi 1 1 is equal to 100 minus 10 90. Because in the equation number n6, if you see n2, here phi 1 1 remains, phi 3 1 value. What is the phi 3 1? Yeah, phi 3 1 is equal to 10. And phi 2 2 is interior node. Phi 2 0 value, this value is 0. So ultimately phi 1 1 plus phi 2 2 minus 4 phi 2 1 is equal to this 10 right side, this is 100 minus 10 19. In this way, so for the third equation in 3, it becomes phi 2 2 plus phi 1 1 minus phi 4 phi 1 2 is equal to 100, and another in 4 equation will be coming this. So you see that these 4 sets of equation, here only there are unknowns are interior node values. All the equations consist of these 4 interior node values. Okay, so you can write these interior node values into a form of matrix form, or you can update these values either by Jacobi or Gauss-Seidel method to iteratively solve. So there are solution technique through the matrix method that is not involving any iterative method. So that already we discussed, but here again we are just forming the matrix for your understanding. Say this is the matrix we can form in this way. So there is a column matrix consisting of 4 unknown values, phi 1 1, phi 1 2, phi 2 1, phi 2 2. This is the conventionally written. First you write the 1 1, then 1 2, then 2 1, then 2 2 in this way. That's why these 4 interiors are taken and written in this way. And this, there will be 4 row, because this is a one column consisting of 4 elements. So 4 row, 1 2 3 4, and this phi 1 1 into minus 4, you see from the equation, minus 4 into phi 1 1, this minus 4, plus 1 into phi 1 2, this phi 1 2 into 1, plus phi 2 1, phi 2 1 coefficient is also 1, but there is no phi 2 2 coefficient in the n5, so phi 2 2 is 0. So this will be equal to 100. This 100 value is written here. Similarly, in the second equation, you see what is the coefficient of, this is minus 4 phi 2 1. So phi 2 1 means this is minus 4. Or let us start from the initial. So phi 1 1. What is the coefficient of phi 1 1? 1. 1 is here. Then phi 1 2. Phi 1 2 is not present. So this is 0. Then phi 2 1. Phi 2 1 is present, minus 4. Put the minus 4. And then phi 2 2. Phi 2 2 is 1 coefficient. So 1. In this way it is written. So ultimately this is forming an equation. This row multiplied by this matrix is equal to, gives you 100. So 1 into phi 1 1 plus 0 into phi 1 2 minus 4 into phi 2 1 plus 1 into phi 2 2 is equal to 100. That is nothing but this equation. Perhaps you know this way you can represent in the matrix. Similarly, for this row also, by putting this, you can say this is the equation we found. This row, and for this row, these 4 rows represent 4 equations. Now this equation can be solved by Gauss elimination method. Gauss elimination method, mainly first your target is to reduce the off diagonal elements to 0, to change the off diagonal elements to 0 as much as possible. So then solution will be easy. Just like solution we have done in different techniques, elimination method and other techniques. In this way you can solve and you can find out the values of these 4 interior unknown values, phi 1 1, phi 1 2, phi 2 1, phi 2 2. So this is the method. But for iterative method, you have to start differently from these 4 equations. So in next class, we will discuss these 4 equations, starting from these 4 equations, how we proceed the iterative method to solve the values of phi 11, phi 12, phi 21 and phi 22. So in this lecture, we have shown by taking an example of a semiconductor device portion how to solve the 2D Poisson equation. We have discretized and we have used the mesh notations. The 5-point formula for the second order derivative in two-dimensional. We have discussed how to frame the node equations and iterative method principles for Jacobi, Gauss-Seidel, SOR we have discussed, and mesh and updates of node values have been discussed in principally, but we have not shown by taking example, so it is not covered here. But in the next class, from the node equation whatever we obtained, we will start to show how the iterative method will be used to solve these interior node values. This is again reference. Thank you.